All right, in this last section on circle proof, we'll talk about developing proofs using the theorems that we've learned in the last few lessons. All right, so in number 1, let's jump right in here. It says, given line segment AC that is tangent to circle O at point A and tangent to circle P at point C. So if I go take a look at what's going on in the picture here, here's line segment AC. I notice that it intersects radius OA at point A. And I also know that where the tangent meets the radius, a right angle is formed. So I know that angle A is a right angle. And likewise, where the tangent meets the radius, a right angle is formed. I also know these vertical angles at point B are going to be congruent. So if what we're trying to prove is that angle O is congruent to angle P, I see a lot of different options that are available for this. We could say anytime you have 2 angles in one triangle, congruent to 2 angles in a second, the third angles must also be congruent. We could use angle-angle similarity to prove that these 2 triangles are similar. And once those 2 triangles are similar, we know that all of their corresponding angles have to be congruent. That would be a second possibility. I'm going to use a third possibility that has to do with parallel and perpendicular lines. I'm going to use the fact that segment AC is perpendicular to both OA and CP to establish the fact that these 2 lines are parallel. And if these 2 lines are parallel, then these guys must be congruent, because anytime you have parallel lines, alternate interior angles are congruent. But again, you could use the similar triangles. You could use the fact that anytime 2 angles of one triangle are congruent to 2 angles of a second, the third angle has to be congruent as well. All right, so I'm going to go ahead and develop this proof. I'm going to start with line segment AC that's tangent to circle O at point A and to circle P at point C. That's a given. I'm going to go ahead now and say that segment OA has to be perpendicular to segment AC, and that segment PC has to be perpendicular to segment AC. And that's because a radius drawn to a tangent is always perpendicular to that tangent. And now, because segment OA and segment PC are both perpendicular to segment AC, I can go ahead and deduce that segment OA has to be parallel to segment PC. And that's because anytime you have 2 lines perpendicular to the same line, they are parallel to each other. And then lastly, once these 2 lines are parallel to each other, I know that alternate interior angles have to be congruent. And I hope you're seeing this in the diagram or in the picture. But if you don't, those lines, red lines are my parallel lines. That purple segment is the transversal. So the angle at O and the angle at P are the pair of congruent alternate interior angles. So angle O is congruent to angle P. And that's because anytime you have parallel lines, the alternate interior angles are congruent. So regardless of how you write that proof, it really is a nice integration of our knowledge of circles together with, in this case, our knowledge of parallel lines. Or if you wrote the proof using similar triangles, our knowledge of similar triangles. But again, it's really pulling together all these ideas that we've worked so hard to develop throughout the course of the year. All right, number 2 says, given circle O with diameter AC, They're telling us that they're extending diameter AC in such a way that the angles at D is a right angle, or that the lines are perpendicular. And they're asking us to prove that the product of segment AF and EC is equal to the product of AC and FD. All right, so anytime I see this product here, I'm going to think to myself, similar triangles. Why? Well, similar triangles have corresponding sides that are in proportion, and it's by cross-multiplying the pieces of that proportion that we end up with the product in the proof. So again, that tells me to think similar triangles. And when I go to look at the picture, you might say, well, which triangles? Well, AF has to be a side in one of the two triangles. So I'm going to use my red pen and I'm going to highlight segment AF. EC has to be a side in one of our triangles. That's in a different triangle than AF. I'm going to make it a different color. AC, segment AC is in the same triangle as segment EC, so I'm going to make that green. So now I know that one of my triangles is AEC, and then the other triangle, FD, is going to be the second side. So I can see that the other triangle that I'm trying to prove that similar to is the red triangle. So I want to prove the red triangle similar to the green triangle. I can see immediately by looking at the picture that they share this angle here. I know that the angle at D is a right angle, so I'm going to go look at the green triangle for a right angle. I know that angle E is inscribed in the semicircle. In looking at this picture, AC is a semicircle. Angle E is inscribed in that blue arc. Any angle inscribed in a semicircle has to be a right angle. So I know that angle at point E has to be a right angle. So the gist of how I'm going to write this proof is I'm going to prove the red triangle similar to the green triangle using angle-angle similarity. Once I establish the fact that the triangles are similar, I'm going to write their corresponding sides in proportion. And then lastly, I'm going to cross-multiply the proportion in order to get the statement that I'm trying to prove. All right, so for all you two-column people out there, I think I will write this one last proof in statement reason form, but if you'd prefer to write the flow proof, then by all means, you're more than welcome to do that. So I'm going to go ahead and start with diameter AC. And I'll just use the language that they gave me in that given. All right, so that's my given. I'm going to go ahead and say right away that angle AEC is a right angle. And that's because any angle inscribed in a semicircle has to be a right angle. And I'm going to cite statement 1 because statement 1 had diameter AC telling me that arc AC is a semicircle. I also know that angle D is a right angle. And that's because anytime you have perpendicular lines, they meet at right angles. And I'm going to cite statement 1 again because statement 1 is where I had those perpendicular lines. And the next step, I'm going to continue onwards to establish the fact that angle AEC is congruent to angle D. And you know that's because all right angles are congruent. And I'll cite statements 2 and 3 because those are the statements where I had the two right angles. Angle A is congruent to itself by the reflexive property. This is a really great proof to do at the end of the year because it really pulls together a lot of the ideas that we've studied over the course of the year. All right, now I can go ahead and name my two similar triangles. Remember that when you name the triangles to match up their corresponding parts. So for the green triangle, I'm going to say call that triangle AEC. And in the red triangle, angle A matches up with angle A. In the green triangle, angle E was the right angle. In the red triangle, angle D was the right angle. So I'm going to call that triangle ADF. And that's by angle-angle similarity. And I am going to cite statements 4 and 5 because those are the two statements where I had my congruent pairs of angles. And once the triangles are similar, I know their corresponding sides have to be in proportion. So in other words, I know that if I compare side AF to its corresponding side in the larger triangle, the smaller triangle, which is AC, I know that ratio is going to be equal to the ratio between FD in the larger triangle compared to EC in the smaller triangle. And that's because anytime you have similar triangles, they have corresponding sides that are in proportion. And then lastly, in order to wrap this up, I can go ahead and cross multiply. So the product of AF and EC is going to be equal to the product of AC and FD. And that's simply cross multiplication. And I want to make sure I go ahead and cite statement 7, where I have the proportion that I cross multiplied. And I didn't cite in statement or reason 7. I want to go back up and cite statement 6, because statement 6 was where I had those triangles that were similar. All right, again, I think this is a really nice way to end up because it brings back all those ideas that we studied in similar triangles. I'm going to, as always, make sure you take some time to reflect on what you saw and what you heard in this video. If there were things that I said that didn't make sense, go back and rewatch the video. But again, take that time to think about what you watched and what are the important understandings and the key ideas that you pulled away from that video. And then, of course, see if you can apply what you know to write the proof on the following page.